Hello, this is Ferhat Tigrek. In this screencast, I will introduce the concept of estimator bias and variance, and then I will introduce the Kramer-Raoul overbound. First, let's set up a problem. I have an electric car, which I charge every now and then. I would like to know how much energy the car consumes per kilometer traveled. I keep a record of the readings from the charging station versus the distance I traveled since the last charging. So, I can calculate the average energy consumption from the data at hand. We have another screencast where we develop the least squares estimator for the energy consumption problem. The idea behind the least squares estimator is to fit a line to all the data points at hand. The squared error term tells the discrepancy between the data and the model, and we find the best fitting model by minimizing the squared error term. However, there is one caveat here. The data has a random component. Every time we get a batch of data records, it will be different from the previous ones. So every time I run my least squares estimator with a new record batch, I will get a slightly different estimate. But how slightly different? Let's consider an experiment. I set up a simulation that generates independent datasets according to the data model on the screen. I have a signal model, which is controlled by the parameter theta, that is the energy consumption per kilometer. On top of that, I have noise. For the least squares estimator, we did not care much about the noise, but it has a profound effect. Let's see the outcome of our least squares estimate for a bunch of independent data records. Each data record consists of 10 entries, and we find the least squares estimate of the controlling parameter. As the estimations come in, we record them to a histogram to observe the frequency of occurrence. This experiment continues for quite some time. It covers 1,000 data records of 10 entries each. So let's fast forward to the end. We observe that the estimate theta has quite some variability. The estimate is in essence a random variable itself. So for any given data batch, there's a chance that our estimate is off the actual value quite significantly sometimes. But how often are we off quite significantly? And how can we reduce the variability of our estimation? To answer these questions, we consider the bias and the variance of our estimate. To consider bias, we focus on the same example. We repeat the same experiment with one significant difference. We use a different noise model. The histogram for the least squares estimate of the parameter theta is presented on the right-hand side figure. The experiment concerns the same signal model as with the previous experiment. The energy consumption is the same for both experiments. What happened here? If we were to find the estimate of the parameter theta by taking the peak of this histogram, we would end up with an offset. The mean of the histogram would be no better. Let's keep the outcome of the two Monte Carlo simulation outputs side by side to clearly see the differences and contemplate on two fundamental questions. How do we manage the bias and variance of the estimate? And what is the best performance we can obtain for a given problem setting? Obviously, we can run simulations to understand the behavior of the estimator. We may also derive the bias and variance of the estimate. For this screencast, let's limit our scope to simulations because we already developed the tools. Also, let's focus on the zero mean Gaussian distributed noise, the unbiased case according to the first simulation. We can try a couple of parameters. We can change the size of the data batch. We can modify the noise, or we can try different parameter values. The histograms you see on this screen are generated by varying the data batch size. The more samples we have in our data batch, the sharper the histogram becomes. So the variance of the estimate is reduced. Let's continue exploring. Increasing the noise variance also increases the estimation variance. Here we should note a very important caveat. The variance value we come up with based on these simulations is itself an estimation of the actual variance. We can calculate the actual variance for the estimator based on the data model and noise distribution. So, the question that matters the most, Is there a best estimator we can come up with that has as low a variance as possible? Can we have an estimate with no variance at all? The answer to this question is the Kramer rollover bound for unbiased estimators. Basically, if an estimator is unbiased, then the variance cannot be lower than the inverse of the Fisher information, which is related to the log likelihood function. The detailed treatment of Kramer rollover bound is given in the lecture notes. Now, let's plot the variance of the estimate against the Kramer rollover bound we calculate for different noise variance values. I will not provide the math to calculate the Kramer rollover bound. You can find the formulation of the Kramer rollover bound in the lecture notes. But I would like to emphasize 3 key points. First point, to calculate the Kramer rollover bound, you need 2 essential components: the signal model and the noise probability density function. The second point, the Kramer rollover bound does not give you a minimum variance unbiased estimator. It gives you the lowest possible estimation variance an unbiased estimator can achieve, which depends on the signal model and the noise probability density function. The minimum variance unbiased estimator is well defined for linear signal models with zero mean Gaussian noise. Such problems will be investigated in another module. Third point, the Kramer rollover bound is only valid if the underlying probability density function satisfies the regularity conditions. What are these regularity conditions? I need to give a fair warning here. To appreciate this slide and the next one, you need to be familiar with the log likelihood function and the score. There is a separate screencast regarding the likelihood function, and the score is described in the lecture notes. Now, the need for regularity conditions arises from a particular step in the derivation of the Kramer rollover bound, and this step concerns the score and the expected value of the score. The derivative identity concerning the natural logarithm, combined with the fact that the likelihood function is nothing but the probability density function, leads to a simple expression where there is a derivative operation inside an integral. The regularity conditions allow switching the order of differentiation and integration, which means we are taking the partial derivative of the integral of a probability density function over all sample set. That integral is equal to 1, and the derivative of 1 is simply 0. Thus, the expected value of the score equal to 0 if the regularity conditions are satisfied. So what are these regularity conditions that allow us to switch the order of the differentiation and integration in this derivation? One regularity condition is the probability density function has to be non-zero for an interval of values that is independent of the parameter theta. An alternative regularity condition concerns probability density functions that are non-zero for all values of x and continuously differentiable and their integral converging for all theta. And yes, these definitions are somewhat abstract. So let's see an example to appreciate the meaning of the regularity conditions. Let's consider the Gaussian probability density function with zero mean and variance equal to 1. The Gaussian function is very well behaving. It is continuous and differentiable for all values of x. It is non-zero for all values of x too. So what about the derivative with respect to the controlling parameter theta? Or what about the integral over x for different values of theta? We need a signal model to judge that property. Let's consider the DC voltage level in noise as the signal of interest. The parameter theta controls the mean of the Gaussian probability density function in that case. The likelihood function, which is the probability density function controlled by the parameter theta, is plotted on the right-hand side. Shifting the Gaussian probability density function by modifying its mean does not change the value of the integral over x. It's still equal to 1. Moreover, the likelihood function is continuously differentiable in theta. So we can switch the order of the partial derivative and the integration to obtain the expected value of the score equal to 0 for this particular problem setting. With this slide, we conclude this screencast. If you have any questions about this screencast, please contact us. Have a nice day.